In our earlier video, we had learnt about ionization energy and its exam style questions. And in this video, we'll be learning about factors affecting ionization energy. To understand the factors affecting ionization energy, let's understand these two pictures. In the first picture, we can see that at the center, there is a fight going on in between, and there are so many people. A crowd is surrounded by this fight, and there are few people which are outside the crowd and which are trying to watch the things which are going on at the center. Now we can compare this center with the nucleus of the atom, and the crowd which is surrounding here can be compared with the electrons which are present here around the nucleus, but they are inside. And the people which are outside the crowd can be compared to the electrons which are in the outer shell of the atom. Now let's think of the reason that why the people who are outside the crowd won't get attracted to the center and will try to move away from the crowd. So the first reason may be that the distance of these outer people from the center may be so far, maybe the distance is so much that they are not able to get attracted to the center and they try to move away because they are not attracted to the center. The second reason may be that there are so many people, there's lots of crowds in between which is hindering them to see the picture which is getting at the center. Or whatever is happening at the center is not strong enough to attract the outer people in the crowd. So comparing same in the second picture here, if outer electrons are far off from the nucleus, then the attraction force for this outer electron towards the nucleus is not strong enough. So one of the factor can be the distance between the outer electron and the nucleus. And so electron may release out easily. Secondly, there are many electrons in between which shields the outer electron from the nucleus. This shielding effect again decreases the attraction between the outer electron and the nucleus, and again the outer electron may release out easily. And thirdly, the nuclear charge is not strong enough to attract the outer electrons, and this may again help the outer electron to release out. So we can summarize that the factors affecting the ionization energy may be the first one, distance of the outer electron from the nucleus. That is, if the distance is greater, then the ionization energy required to release out the energy is less. Second factor is the size of the nuclear charge. That is, if greater the nuclear charge, higher is the ionization energy. The reason is that if there are more number of protons inside the nucleus, then the energy required to remove out the outer electron is very high. And the third factor is shielding effect of the inner electrons. That is, if the inner electrons are very high, that is the shielding effect is very high, then the ionization energy required to remove out the electron will be lesser, because this inner electron will be shielding the outer electron to get attracted towards the nucleus. So these are the three factors which affects the ionization energy. So it can be summarized as higher the distance, lesser will be the ionization energy. If the size of the nuclear charge is greater, that is the higher atomic number, higher will be the ionization energy. If shielding effect is high, then ionization energy will be low. Now next, let's study this table where these are the name of the elements, and this table represents the successive ionization energies. That is, what's the energy required, what's the first ionization energy required when the first electron is removed, what's the second ionization energy, third ionization energy, and respectively for different elements given in the first column. Now let's compare the first ionization energy of hydrogen and helium. We can see that the helium has higher first ionization energy. Though both hydrogen and helium have only one shell and both the electrons are added in helium in the first shell itself. But the difference is hydrogen have only one proton but helium have two protons. So we can compare the nuclear charge of helium is very high, and because of that the ionization energy of helium is greater than the ionization energy of hydrogen. Now if we compare the first ionization energy of lithium, we can see that it is much lower than the first ionization energy of helium and hydrogen. Now if you compare the electronic structure of lithium with the proton number 3, we can see that its electronic structure is 2 and 1. While in helium, it's only 2 and hydrogen, it's only 1. That shows that lithium have the outer electron in the second shell, while in hydrogen and helium, both have the first electron which are getting removed are in the first shell, which are very close to the nucleus. So we can see that as the outer electron is very far from the nucleus, so the ionization energy needed to remove out this electron is less compared to the first ionization energy of hydrogen and helium. We can also see that the outer electron of lithium is shielded by 2 electrons in the first shell. So shielding effect is also greater, and because of that the ionization energy, first ionization energy of lithium is low. Now if we compare the successive ionization energy of lithium, that is second and third ionization energy of lithium, we can see that the successive ionization energies keeps on increasing, and there is a big difference between the first and the second ionization energy. The reason being is that once this outer electron is removed out, then now the second electron has to be removed from the first shell, which is closer to the nucleus. And there are no electrons in between to shield this second electron. That's the reason that the second ionization energy is much greater than the first ionization energy. Now comparing the first ionization energy of lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon, we can observe that there is a general increase going along the period because these are the elements which are lying in the same period. There is a general increase in the first ionization energy of these elements of the same period, with only 2 exceptions here. The reason for these exceptions we'll be learning in the next video, but if we look at the general increase along the period, then first let's have a look at their electronic structure. Lithium have 3 proton number, that is 3 atomic number, and so its electronic structure is 2 and 1. For beryllium, the atomic number is 4, and so its electronic structure is 2 and 2. For boron, the electronic structure is 2, 3. For carbon, the electronic structure is 2 and 4, and so on. So we can see that the electron which is added with each successive element is added in the same second shell because all these elements belong to the second period. That shows that the distance of the outer electron from the nucleus remains reasonably same, and the shielding effect, that is the inner 2 electrons, also remains constant in all the elements along the period. But there is a increase in the atomic number, that is the increase in the nuclear charge can be observed along the period. So due to increase in the nuclear charge, the ionization energy also increases. Now let's compare the successive ionization energies of carbon. We can see that the successive ionization energy gradually increases from first to fourth. But between this fourth ionization energy and fifth ionization energy, there is a very high jump. Now if you compare the electronic structure of carbon, we can see that the electronic structure is 2 and 4. So that shows that to remove out one electron every time, the ionization energy increases because of the increasing effective nuclear charge. But now next, when the fifth electron is removed, this electron is removed, that has to be removed from the first shell, which is much closer to the nucleus. So because of that, the fifth ionization energy is very, very high. And this happens in each and every element, that once the outer electrons are fully removed, and the next electron is to be removed from the next shell, which is closer to the nucleus, we will observe a very big jump in the ionization energy. From all these observations, we can interpret few points about the successive ionization energies. That is, when the first electron is removed, it has a very low ionization energies compared to the other electrons which are removed successively later on. So, the second electron which is removed has a higher ionization energy compared to the first ionization energy, because it is difficult to remove the second electron because of the increased effective nuclear charge, because the number of protons remains same, but now the number of electrons are lesser, and as the number of electrons are less, the attractional force between the nucleus with the same proton number will be much higher for the electrons which are less in number now. The successive ionization energies of any element can be used to confirm the number of outer shell electrons, and hence we can also find out the group of that element. This we have already studied in the case of carbon. And hence the successive ionization energy can also be used to predict the electronic structure of the elements. Let's understand this with the help of an example. This example says that the first 6 ionization energies of 4 elements A to D, that is A, B, C and D, are given here. Now the question is, which element is most likely to be in group 4? Now as we know that from the successive ionization energies we can predict the group number. The reason being is that if the element is in group 4, then there should be a gradual increase in the first 4 ionization energies, and then the fifth ionization energy should be very, very high, because the fifth electron is in the next shell, which is much closer to the nucleus. So if you compare the first 4 ionization energies of these 4 elements, we can see that there is a gradual increase in the elements of element A and B between 4th and 5th ionization energy. But for element C, the increase in the ionization energy of 5th is much higher compared to the 4th ionization energy. So our answer should be C, because an element which is in group 4 should have a very big difference in the ionization energy between 4th and 5th. Along with this, let's also understand the trend in the ionization energies down the group and along the period. If we study the trend in the ionization energy down the group, we can see that the ionization energy decreases down the group. We have already studied that in our earlier table when we had compared the first ionization energy of hydrogen and lithium. But still, if we compare the ionization energy of hydrogen, we can see that there is only one electron in the outer shell of hydrogen with only one shell. But lithium have two electrons in the first shell and one electron in the second shell. If we look at sodium, sodium have two electrons in the first shell. It has fully filled second shell with 8 electrons, and it also has a third shell with 1 electron. Now if we compare the first ionization energy of all these elements which are in group 1, we can see that the first electron of hydrogen is very close to the nucleus with no shielding electrons. But in lithium, the outer electron, that is when first electron is removed out, that is little farther from the nucleus compared to hydrogen, and it also has two inner electrons which are shielding this outer electron. And in case of sodium, the outer electron is much farther from the nucleus, and also there are many more electrons which are shielding these outer electron from the nucleus. So these two factors decreases the first ionization energy down the group. That is, the distance between the nucleus and the outer electron increases, so ionization energy decreases. The shielding effect of the inner electron increases down the group, and so ionization energy decreases down the group. Also, there is an increase in the nuclear charge, but these two factors outweighs the increased nuclear charge, and because of that, the ionization energy decreases down the group. Now let's also study the trend in the ionization energy along the period. Along the period, there is a general increase in the ionization energy, and we have seen this in the elements of the second period. The first reason is the distance between the nucleus and the outer electron remains reasonably constant. The shielding effect of the inner electron also remains the same because the outer electrons are added in the same shell. But nuclear charge increases along the period, and because of that, the ionization energy also increases, which is to overcome the increased attractional force from the nucleus to the outer electron. Now let's understand all this with the help of some more exam style questions. The second example is the first ionization energy of fluorine is 1680 kilojoules per mole, whereas the first ionization energy of chlorine is 1260 kilojoules per mole. So explain the trend. Now we know that fluorine and chlorine are both in the same group, that is group 7 of halogens. So both of them have the 7 electron in the outer shell, but fluorine is in period 2 and chlorine is in period 3. That is, the 7 electrons of fluorine are in second shell, but 7 electrons of chlorine are in third shell. So the first electron of fluorine has to be removed from the second shell, but first electron of chlorine has to be removed from the third shell, which is farther from the nucleus compared to fluorine. So we can explain this trend with the help of these 3 points, that the distance of the nucleus and the outer electron increases from fluorine to chlorine. That is, the outer electron of chlorine is farther from the nucleus compared to fluorine. The shielding effect for chlorine by the inner electrons is also greater compared to fluorine, and because of these two factors, the increased nuclear charge loses its effect. So down the group from fluorine to chlorine, the ionization energy decreases. The third example is the first ionization energy of sodium is 494 kilojoules per mole, whereas the first ionization energy of magnesium is 736 kilojoules per mole. Now we know that sodium and magnesium both lies in the third period. That is, both the sodium and magnesium have 3 out shells of electrons. But the difference is that the sodium has 11 protons and magnesium have 12 protons. So you can see that the first electron from sodium or magnesium has to be removed from the third shell itself. So the distance of the outer electron to the nucleus is reasonably same. The inner shell has the similar shielding effect. So only difference is that the nuclear charge of magnesium is greater than the nuclear charge of sodium. So we can explain this trend of the increase in the ionization energy along the period with the help of these 3 points, that the distance between the nucleus and the outer electrons remains same for both sodium and magnesium because they lie in the same period. The shielding effect of the inner electrons for both sodium and magnesium is also same. But the nuclear charge increases from sodium to magnesium, and so because of that, the ionization energy also increases for magnesium to overcome the increased attractional force from the nucleus to the outer electron. So in this video, we have learnt about the factors affecting the ionization energies. From the successive ionization energies, what can we predict? And also we have learnt the trends in the ionization energy down the group and along the period.